Okay, so this is week 5. I'm going to deal with probability. So let's start with some definitions. Probability. So this is a chance that a specified outcome will occur, expressed as a number between 0 and 1. It never includes a percentage sign, so do not include those in an answer. So it has to be a number 0 to 1, so 0.5, 0.8. It's not going to be 58%. It's 0.58. That's what you need to do. Now, an experiment. An experiment is any observation of a random phenomenon. Now, outcome. The different possible results of the experiment are called outcomes. Sample space. The set of all possible outcomes is called the sample space S. Now, N of S is the total number of outcomes in the sample space. Then we have events, and event E is any possible outcome of an experiment. N of E is the number of outcomes in event E. Now we have some complement rules. Now P of E is the probability the event E occurs. And so when you have just the P parenthesis, the E and parenthesis, you have to read it as the probability that event E occurs. So then if you have not E in there, that's the probability that event E does not occur. And sometimes that's E complement with the E prime here. Okay. So the complement rules of probability are, if we take probability of E plus the probability of the complement, that's going to equal 1. Or we can rearrange this in two other ways. We can say the probability of the complement of E is equal to 1 minus the probability of E, or the probability of E is equal to 1 minus the probability of the complement. So for example, if you're dealt one card from a standard 52 card deck, find the probability that you're not dealt a diamond. Well, so probability that we have the E complement, the probability we are not dealt a diamond. So probably is easier if we find probability of E, the probability that we are dealt a diamond. Well, how many diamonds are there? Well, there's 4 suits. One suit is 13 cards, and so 13 of them are going to be diamonds. So 13 out of those 52 are going to be diamonds. If we reduce that, that's 1/4. So the probability that we're not dealt a diamond is going to be 1 minus that 1/4, or 3/4. So the probability we're not dealt a diamond is 3/4. Theoretical probability and the classical approach. So with theoretical probability, if an event E has N of E equally likely outcomes, and its sample space S has N of S equally likely outcomes, the theoretical probability of event E, denoted by P of E, is P of E, which is the probability of E occurring, is the number of outcomes in event E divided by the total number of possible outcomes. So that's just going to be N of E divided by N of S if you write it in the numerical way. So, for example, what would be the theoretical probability of getting the tail when tossing a coin? Well, we have to think about the event. So the number in the event is 1 because the event is getting a tail. So the event is just the set with T, getting a tail. But what is the sample space? Well, number in a sample space is 2 because we have S, which is the sample space. You can either get a head or a tail when you toss a coin. So there's 2 possible ways when you toss the coin. We have only looking at the event with the T, and so we divide those. So N of E is 1, N of S is 2, so 1 divided by 2 is 0.5. And it's also okay to write it as a fraction, as long, again, that number has to be between 0 and 1. Now, empirical probabilities, the relative frequency approach. Here, empirical probabilities of an event E is given by P of E equals the observed number of times E occurs divided by the total number of observed occurrences. So, for example, if we toss a coin 1,000 times and we get 495 heads and 505 tails, what is the probability that we will get a tail? Well, how many times did we get a tail? We got 505 of them. And how many times did we toss the coin in total? 1,000, so 505 divided by 1,000. So the probability of a tail is 0.505. So that's kind of the empirical probability, kind of what you observe. Now, probability to odds. So this is kind of more about gambling here. Now, if the probability of E is the probability of event E occurring, then odds in favor of E are found by taking the probability that E will occur and divide by the probability that E will not occur. So odds in favor, if we're given P of E, then we take P of E divided by P of not E. Okay. And odds against are found by taking the probability that E will not occur and divide by the probability that E will occur. And so odds against E is probability of not E divided by probability of E. And again, remember, not E is the E complement, so I'm trying to represent the not E and E complement in different ways, so you realize it can be used different ways. Now, the odds against E can also be found by reversing the ratio representing the odds in favor of E. So if we know the odds in favor, say it's whatever it is, then you can just reverse them and then it'll be the other way around. So let's look at an example here and on that. So you're dealt one card from a 52 card deck. Find the odds in favor of getting a red queen. So our event is getting a red queen. Well, how many red queens are there? Well, there's going to be just two, because you're going to have two reds and you're going to have two blacks. So the odds in favor of E is going to be the probability that we have event E occurring divided by the probability that event E does not occur. So how many red queens? There's 2 out of how many total cards? 52. So that's going to be the probability of E occurring. Now, probability that E does not occur, well, that's going to be what's left, 50 divided by 52. So we're going to take this divided by this. That gives us 2 divided by 50. Reduce that to 1 over 25. And so we can represent the odds in favor of getting the red queen as 1 divided by 25, or 1 colon 25, or 1 to 25. And the way you would say all of them is 1 to 25. Now you could find the odds against it by just reversing this and say 25 to 1, 25 colon 1, or 25 to 1 here. So you can go either direction. Now we can also go from odds to probability. So if we know the odds now, instead, we can go back to probabilities. So if the odds in favor an event E are A to B, then the probability the event is given by probability E equals A divided by A plus B. And again, all we're worried about is that odds. Okay. Now remember, it's odds in favor. So what do we say over here? Well, if we're given odds against, we just reverse it and we have odds in favor. So if we're given odds against, then we just have to switch those around to make it odds in favor. So say the odds in favor of a particular horse winning a race are 2 to 5. What is the probability the horse will win the race? Well, A is 2 in this case because it's A to B. So A is 2, B is 5. So we just plug in here 2 divided by 2 plus 5. So that's 2 over 7. And that's going to be a probability that event E occurs. Now, when you have numbers like this that are not going to be nice decimals, sometimes it's more accurate to leave it as a fraction. So that's why I left this as a fraction, because it's more accurate than actually dividing it out, because then you'd have to round. All right, mutually exclusive events. If it is impossible for events A and B to occur simultaneously, the events are said to be mutually exclusive. Or, which is represented by the union probabilities with mutually exclusive events. If A and B are mutually exclusive, the ME, then probability of A or B is equal to the probability of A plus the probability of B. And again, we can write the or as a union, and so we can say probability of A union B is equal to the probability of A plus the probability of B. So for example, if you roll a single 6-sided die, what is the probability of getting either a 4 or a 5? All right, so can you roll a 4 and a 5 at the same time? No, so these are mutually exclusive, and so we can use this format here. Probability of a 4 or a 5 is equal to probability of 4 plus the probability of 5. Well, what is the probability of each one of those? Well, how many sides are there? There's 6 sides. There's only going to be one number out of those 6. So each one of these is going to have a probability of 1/6. So what we have is probability of 4 or 5 equals probability of 4 plus the probability of 5, and that's equal to 1/6 plus 1/6, which is 2/6, and we can reduce that to 1/3. And again, as a decimal, that's not very nice, and we won't have an exact probability if we do any rounding, so we'll just say it's 1/3. All right, events that are not mutually exclusive. Okay, again, or union probabilities with events that are not mutually exclusive. So if A and B are not mutually exclusive events, then the probability of A or B, or in union, if you want to look at it with unions, is going to be equal to the probability of A plus the probability of B minus the probability of A and B. Or A and B can be represented by A intersect B. So what's an A and B? All right, so here in a group of 50 students, 23 take math, 11 take psychology, and 7 take both math and psychology. If one student is selected at random, find the probability the student takes math or psychology. Okay, so already we know that there's going to be some of them taking math and psychology, so we have this and part here, and it's not mutually exclusive. So if we want to find a student takes math or psychology, we have to take the probability of math plus the probability of psychology minus the probability of math and psychology. So what we have to do is we have to find what those probabilities are. And so for probability of math, how many math students were there? There were 23. Well, probability is going to be 23 out of 50 because we have 50 total students. And so the probability of math is 23 out of 50. Now, psychology, there's 11 of them out of 50, so that's going to be the probability of B, and so it's going to be 11 out of 50. Now, 7 of them take both math and psychology, so 7 out of the 50. That's going to be what we subtract off, the probability of math and psychology. So if we do the math there, we end up with 27 out of 50 for our final answer for the probability of math or psychology given these conditions. Probabilities. So marginal probability. The probability a given event will occur. No other events are taken into consideration and is usually expressed as probability of A. Okay, so it's kind of like what we've been looking at, the probability of E. We have joint probabilities. The probability that 2 or more events will all occur expressed as probability of A and B. And then we have something called conditional probability. And the probability that an event will occur given that another event has already happened is expressed as probability, and this is written A given B has occurred. So a perpendicular line is given that, and so probability of A given that B has already occurred is what that means. And the probability of A given B is equal to the probability of A and B divided by the probability of B. And here B cannot be equal to 0, so the probability of B has to be greater than 0. And the other way around, probability B given A is equal to the probability of B and A divided by the probability of A, where probability of A has to be greater than 0 as well, because you can't have 0 in the denominator. Now, probability events. We have independent events and dependent events. 2 events are independent if the occurrence of either of them has no effect on the probability of the other. Now, 2 events are dependent events if the occurrence of one of them has an effect on the probability of the other. So independent events first. Let's look at AND probabilities with independent events. So if A and B are independent events, then probability of A and B, or the probability of A intersect B, is equal to the probability of A times the probability of B. Okay. Now, the nice thing about the independent events like this and doing AND, you could have multiples. You could take a probability A and B and C and D and E. You can find the probability of all that, and all you do is you just keep multiplying their probabilities together. And that's what we're going to do with this example. So find the probability of a family having 4 boys in a row. All right, well, what is the probability of getting a boy? Well, it's 1/2. Okay. So what we're going to do is probably 4 boys. So instead of writing out boy and boy and boy and boy all the 4 times, I just put 4 boys, but it really is boy and boy and boy and boy until you hit 4. And so that's just going to be 1/2 times 1/2 times 1/2 times 1/2, because each time the probability is 1/2, and the probability is not dependent on if the first one is a boy. You're not going to have the same probability here. They're all equal to 1/2, and when you multiply that together, you get 1/16. Now, dependent events and probabilities with dependent events. So if A and B are dependent events, then probability of A and B, or their intersection, if you want to look at it that way, is equal to the probability of A times the probability of B given A. Okay, and again, the probability of B given A is the conditional probability that we saw earlier. So for example, if you're dealt 2 cards from a 52 card deck, find the probability of getting 2 kings. So we're going to find the probability of getting basically here king 1 and king 2. So we have to kind of differentiate them. And so what is that going to be? Well, it's going to be a probability of king 1 times the probability of king 2 given king 1. Okay. Well, what is the probability of king 1? Well, there's how many kings? There's 4 kings. Out of how many cards are there in a deck? 52. So the probability of getting 1 king out of that deck, that king 1, is going to be 4 divided by 52. But now we have to find the probability of king 2, given that we already drew king 1. Well, if we already drew king 1, what does that mean? Well, that means we've reduced the total number of kings from 4 to 3, and the total number of cards from 52 to 51. So that's the probability of king 2 given king 1. And all we have to do, it says, is multiply those together. So we get 12 over 2652, and that reduces to 1 over 221. And again, that's the accurate answer. You could go ahead and put it into the decimal form, but unless it says to put it into the decimal form to 4 decimal places or whatever, the fraction usually is the more accurate way to go. Okay, some more conditional probability. So a cooler contains 8 bottles of Guinness Extra Stout, 12 bottles of Samuel Adams Dark Lager, and 3 bottles of Budvar Budweiser Czech Premium Lager. So let E be the event that the first bottle selected is a Guinness Extra Stout. Then let F be the event that the second bottle selected is also a Guinness Extra Stout. So we want to find the probability of F given E occurred. Okay. So what we need to do first is find out the total number of bottles of beer we have in the cooler. So if we add the 8, the 12, and the 3, we should get 23. And then we have to find the probability of event E. Well, event E was, again, drawing that first Guinness out of the 23. So that was going to be 8 out of 23 because there's 8 bottles of Guinness, 23 total bottles. So that's the probability of E. Now, after we finish that bottle off, we reach into the cooler again. How many bottles are left? Well, now there's only 22 because now we are left with 7 Guinness, 12 Sam Adams, and 3 Budvars. And so that's 22. And so now we find the probability that we draw another Guinness. And so now that's going to be 7 divided by 22. And so that probability of F given E is equal to 7 over 22. Again, the F was the event, the second bottle was a Guinness, given that we drew the first bottle was a Guinness. All right, example. So a survey reveals that 54% of people enjoy watching hockey, 34% watching rugby, and 28% both hockey and rugby. What is the probability that a person will enjoy watching hockey given that the person enjoys rugby? All right, so we have that given. So that means we have a conditional probability. So we want to find some probability of B given A, okay? And in this case, what we have to do is, the way it's set up is we're going to use numbers because we have percentages, so those are kind of like numbers. So the probability basically of B and A, okay, well that's 28 because we have 28% enjoy both hockey and rugby. And that's going to be divided by the number in A. Well, again, what was A? Well, that's the rugby. And so how many liked rugby? That was 34%. So 28 divided by 34, we can reduce it to 14 over 17. Or if this time, say they wanted it to 3 decimal places, 0.824. Okay, so sometimes you're going to have to go from percentages and therefore just use the numbers, and then you can get your probabilities from there. Now, Bayes' theorem. Now, this is actually for next week, but since this whole thing is kind of one chapter, I went ahead and I'm including it here, but it is actually going to be for your next week. So Bayes' theorem. So Bayes' theorem for the revision of probability. So events A and B. So probability of A given that event B occurred is probability of A given B equals probability of A and B, or at the intersection if we wanted to, divided by probability of B. And we can extend that further and say, oh, well, that's equal to the probability of A times the probability of B given A, all divided by, and then we have the probability of A times the probability of B given A, plus the probability of A complement times the probability of B given A complement, okay? And that's when there's just 2 events. That's what it is there. Now, a general form is more along the lines here, okay? So we have I different events, okay? And so the probability of A sub I given B is equal to the probability of A sub I and B divided by probability of B. And so then we just have the similar kind of numerator, probability of A whatever I is, times the probability of B given AI all over the sum of, and then you just have basically each one of those for the different values there with I. Okay. And so let's look at an example of this, because when you look at these, it really starts confusing a lot of people. So let's look at something here. And these are from a different book. I just thought they were pretty good examples. So machine A produces 3% defectives, machine B produces 5% defectives, and machine C produces 10% defectives. Of the total output from these machines, 60% of the items are from machine A, 30% are from B, and 10% are from C. Now, if one item is selected at random from a day's production, okay, and what we're going to have is we're going to have a couple questions here. So we need to remember that machine A produces 3% defective, B is 5, C is 10, and the total output of the machine, 60 is from A, 30 from B, and 10 from C. But we can go back and cheat and look at this page too. So what is the prior probability that the item came from machine C? Okay. Well, if it comes from machine C, we know that 10% of the items come from machine C, so that's going to be our prior probability. Okay. And so the prior probability is 0.1 since 10% of the output is from machine C. So we've had to convert it to the probability from the percentage. Now, if inspection finds the item to be defective, what is the revised probability? And so we're going to start using that long equation we looked at on the blue formulas, that the item came from machine C. And we'll call the defective event D. So this means we need to find probability of C given D. Okay, so this is when we have to pull in everything here. So probability of C given D is equal to probability of C and D divided by probability of D. And then we can rewrite that, kind of going back to how this formula works. We're just going to plug in the values we know and label them properly. So then it's going to be probability of C times probability of D given C divided by, and then we have to do the three different things on the bottom. So probability of A times the probability of D given A, probability of B times the probability of D given B, and the probability of C times the probability of D given C. Okay, so really, you know, each one of these is the three different machines, and they're going to have probabilities, so we have to take them all into consideration when finding this probability. All right, so now we have to figure out what do these probabilities represent, okay? All right, so we know that 60% of the items from A, 30 from B, and 10 from C, and then 3, 5, and 10. So the probability of C we found was 10%, so that's 0.1. And the probability of D given C, so the probability that we draw a thing and it was from C, is also 0.1 because it produces 10% of the defectives. Okay, so that's 0.1 times 0.1. Now the probability that it comes from machine A is, well, that was that 60, so that's going to be 0.6 when we convert it to probabilities. And the probability that you draw one from A, that was going to be 3%, so that's going to be 0.03. And then probability of B, that was the 30% one, so that's going to be 0.3. There's 5% defectives from there, so that's going to be 0.05. And then this and this are going to be the same, 0.1 times 0.1. Now we put all this into our calculator and we get 0.233. Now one key item here is a lot of people forget. You really need to put parentheses around the whole numerator and put parentheses around the whole denominator if you're typing this into your calculator or Excel. Otherwise, what will happen is if you do it without the extra parentheses, you'll take that times that divided by this, and then it'll say add on to that this quantity, and then also add on to this quantity, which makes the whole answer completely wrong. So you always want to put the extra parentheses, so you're taking this divided by the sum of all those added together. Okay, so that's using the Bayes theorem. And again, that won't be till next week, and so hopefully getting a little reading on that will help you there. Now kind of going back into stuff we're actually going to be covering this week was called counting. Well, we learned how to count as children by basically reciting numbers in order and count objects such as cars or dolls. Now, this is our most basic and fundamental system for counting. Now, higher level of counting occurs when we seek to count possible outcomes of events that cannot be intuitively visualized as objects in space or a linear sequence in time. So an example would be trying to count the number of possible outcomes from 7 tosses of 4 coins, or how about counting the number of license plate numbers that can be created using 3 letters and 3 numerical digits. So for counting problems beyond a certain level of complexity, systematic counting is actually required. So the first thing we can look at for counting is called the fundamental counting principles. So if we want to perform a series of tasks, and the first task can be done in A ways, the second task can be done in B ways, the third can be in C ways, and so on, then all the tasks can be done in A times B times C times D, and so on until we have all the ways represented here. So you just multiply them all together. And so this really is best represented with kind of a pigeonhole plot. And so this is using the slot diagrams. And so some people call it slot diagrams, some call it pigeonholing them. And so a slot diagram is a series of blank spaces to keep track of the number of ways to do each successive task. So to get the total number of possible outcomes, you multiply the numbers in each of the spaces. All right, so up here, if we want to think about that, let me see if I can make this work. That would be a space, that would be a space, and that would be a space, and so on down the row. And all we're doing is we're multiplying what's in each space. So how many possible Social Security numbers can be made if any number from 0 to 9 can be used in any of the 9 spaces? So basically, we're going to have the 9 spots here that we're going to be able to multiply together. And we'll have what numbers in each spot? Well, 0 to 9, there's 10 numbers there. So there's going to be a 10 in each one of those. So represented like this, it's going to be 10 times 10 times 10, or that's going to be 10 to the 9th. Different Social Security numbers can be created. Okay, and so that's an example of how one can use slot diagrams. Now we'll use them again here in a little while, but that's kind of the most basic sense is you just plug in the numbers, multiply them out. Now, factorial notation. If n is a counting number, so 1, 2, 3, 4, 5, the symbol n with the exclamation mark is called n factorial. And basically that stands for the product of n, whatever that there is, times n minus 1, times n minus 2, times n minus 3, on down until you have n minus whatever, and then times 2 times 1. Okay, and again, that's kind of like the pigeonhole or the slot diagram because you're just multiplying all those together. Now, by definition, 0 factorial is equal to 1. So if we ever end up with 0 factorial, we know that's equal to 1. So let's look at how many ways can 8 books be arranged on a shelf. Well, if we think about this, we're going to have 8 slots, and we'll try to ignore what we have above already. And we're going to put a book on each one of those slots. Well, if we have our first slot here on the left, how many ways can we put the books? Well, if we have 8 books, we can put 8 different books here. So there's 8 possible choices here. But once we put that book, how many books are left? Well, there's only 7 books left, so when we get to the next spot, there's only a possibility of 7 choices here, so that's going to be a 7. After we take away that one, that becomes 6, and so on until we have something that looks like that. Now, if we look at that, that looks like what we have up here, which is going to be 8 factorial, and we can use our calculator to do that. We can just type 8 and then find the factorial key on our calculator, and it gives us 40,320, and we don't have to take 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, because 8 factorial with our calculator or even in Excel will give us the straight answer. Now we're going to use factorials to help solve other kinds of problems. First one is going to be permutations. So if the order of objects being counted matters, so in this case order matters, then we have to use a permutation. So a permutation is an ordering of distinct objects. If we select R different objects from a set of n total objects and arrange them in a specific order, this is called a permutation of n objects taken R at a time. Now the number of permutation of n objects taken R at a time is denoted by a couple different ways. P of n comma R or NPR. Now on your calculator, most likely this is what you'll see, and so that's that's a more common way to see it. Now, the formula to calculate P and R is just going to be n factorial divided by parentheses n minus r parentheses factorial. Okay, so we're just going to take the total number of objects in, plug those in for n. How many are we going to take at a time? That's going to be r, and then that will give us the permutations. And so again, if you put it here, you're going to put the n and the r numbers here, or you might put the n and the r numbers here, depending on, again, which version you're looking at. So how many ways can a coach choose a batting roster of 7 batters from a total of 15 players? Well, here R is 7 and N is 15. So we're going to find P of 15 comma 7, or 15P7. Okay. So since order matters in batting roster, we know we have to use the permutation. So there again, what we just stated in is 15, R is 7, so we plug that in. So we're going to get 15 factorial divided by 15 minus 7 factorial. So that's 32,432,400 ways to choose this roster. So for any coaches out there, if their parents complaining about how their kids in the batting roster, tell them if they can write all the ways that you can choose, 7 batters out of the 15 players, you'll let their kid bat first. So if they can come up with 32,432,400 ways to do the roster, then you'll go ahead and let them bat first. But don't tell them that's how many there are. Now, combinations. Now, if the order of objects being counted does not matter, so here, order does not matter, then we use combination. So basically, it's very similar, except the whole key is the order doesn't matter. So if we choose R objects from a set of N objects, we can say we are computing a combination of N objects taken R at a time. Now, the number of combinations of N objects taken R at a time is denoted by C, N, R, or NCR. All right, so the formula to calculate this is C of N, R is really just the permutation we just found divided by R factorial. Well, we can simplify this into a one equation, and that becomes N factorial divided by R factorial times N minus R factorial. Okay, so again, when you're plugging this in your calculator, you'll want to be sure to put parentheses around all of that, otherwise you're going to have a wrong calculation. So, for example, how many different 7-card poker hands can be dealt from a standard 52-card deck? Well, in poker, order in your hand doesn't really matter. And so here, a combination would work. Okay, so this is our R, this is our N. So we basically plug in our values. N was 52, R was 7, N is 52, R is 7. So we have 52 factorial divided by the quantity 7 factorial times the quantity 52 minus 7 in parentheses factorial. So that gives us 133,784,560 different 7-card poker hands that you could actually come up with when you're choosing 7 cards out of 52-card deck. Let's do a little more complex example. Say a poker hand consists of 5 cards. Find the total number of possible 5-card hands. Find the number of ways in which 4 aces can be selected. Find the number of ways in which 1 king can be selected. Use the fundamental counting principle, basically the slot diagram if you want it, if you wish, and do your answer from part B and C to find the number of ways of getting 4 aces and 1 king, and then find the probability a poker hand consisting of 4 aces and 1 king. All right, so does order matter for poker hands? No. So since order doesn't matter, we're using combinations. So for the first question is, how many possible 5-card hands from a normal deck of cards? Well, it's going to be C 52, 5. And so there's 2,598,960 different hands that we can come up with. Now, how many aces are there? Well, there's 4 aces, and so we're going to have to choose 4 aces. So that's really C of 4 total aces, 4 aces that we're choosing, and that ends up being 1. Pretty simple. Now, on the next one, how many ways can you get 1 king? Well, how many possible kings are there? Well, there's 4, so it's going to be N is 4, R is 1, so C 4, 1, that gives us a total of 4. Now, using the fundamental counting principle, we just plug those into the slots, and so we take, is it working? I just lost my audio and everything else, so let's share screen. Let's go back here. All right, so hopefully this will all tie in together because all of a sudden my internet disappeared and then came back instantly. So, what is the probability of getting a poker hand consisting of 4 aces and 1 king? Well, you take that number 4 down here, divide it by the total number of possible hands, and once you reduce it, you get 1 over 649,740. All right, so now complex examples continued. How many license plates are possible consisting of 3 letters followed by 3 digits if the first letter must be a B and we can use only digits 0 through 9? Well, again, a slot diagram is going to work really well here. So we have 3 letters and 3 digits. So we'll have 3 spaces that are letters, 3 spaces that are digits. First letter has to be a B, so there's only one way we can get that B. So that's a 1. And there's 26 ways to get the next letter and 26 ways to get the next letter because it says we're not taking them out and they're not being used again, so we can use them again. And 0 through 9, that's 10. So we have 10 digits we can put in the first one, 10 in the second one, 10 in the next one, because it says we're not taking any out, so we're putting them all back. Multiply that all together, we get 676,000 license plates possible with 3 letters followed by 3 digits with the first letter being a B. All right, how about this one? A university has 8 male and 6 female instructors. A committee of 7, 3 male instructors and 4 female instructors, is to be chosen to represent the university at a conference. How many committees are possible? All right, so again, we're going to use fundamental counting principle, but first we have to figure out how many males and how many females. What is the probabilities? We're going to get those. All right, so how many males total? Well, total males is N is 8, and we're going to end up with picking 3 of them. So that's going to be a combination because in a committee, unless they specifically say it's president, vice president, and treasurer or whatever, a committee can be just any order, it doesn't matter. So we're going to do combinations. So we're going to go C8, 3. That gives us 56 possible ways to do that. Now, if we have 6 total females, and we're going to choose 4 of those, N is 6, R is 4, and so we have the C6, 4, that gives us 15. And again, using the fundamental counting principle, slot diagram basically, we take that times that, we get 840 different committees that are possible. And that's all I have for this week.